So welcome everyone to this lecture on CMOS MEMS. I will record this lecture and put the recordings online. And then I distribute usually scripts that you can scribble on. I will not distribute electronic scripts, but you have all the methods to transform a paper script into an electronic script. There is easy scan software on every phone nowadays if you need to work purely electronically. I consider the scribbling to be an important part of the learning process, and so hope you will benefit of that too. Yeah, so my name is Oliver Paul. Yeah, some of you know me. Yeah, Jonathan, I know you. Yeah, some other faces I know also. Yeah, I've seen. I expected some other people also who, or is that Mr. Gramlich back there? Hi, good to see you again. Yeah, so I have been giving lectures, concentration lectures every semester now during the past 4 semesters since I was a dean. And so I saw some faces. Yeah, so it's a pleasure to give this lecture, CMOS MEMS again. And before we start, we have to talk a little bit about organization. Yeah, so this is of course a lecture within the concentration area of the MST, Master of Science curricula. Yeah, it was originally for the microsystems engineers, but then it was also open to other curricula like the embedded systems engineering curriculum. Who is microsystems engineer? Okay, who is embedded systems engineer? Okay, is there any sustainable systems engineer here too? So maybe it's not open for them, yeah? Okay, so that's why I put a question mark here, because I wasn't sure. And I will give this lecture in English. Yeah, yes, please. You could enroll, then it is certainly open for you too. Then I should add computer science here. Yes, thank you for pointing that out. Welcome. Yeah, it's a lecture that will run through a number of topics. I will give a brief introduction today about some topics, some generalities, and then some examples so that you have kind of an appetizer. And then we'll talk in chapter 2 about basic technologies. And then we'll deal with different kinds of sensors that are based on or fabricated using CMOS technology, because that's the central thing. MEMS is microsystems, sensing, actuating systems, usually combined with circuitry, and then they're fabricated in CMOS technology. That makes it CMOS MEMS. And I'm pretty much a sensor guy, so I know also about actuation, mechanical movement, capacitive actuation, and so on. But I'm really a broadly educated sensor guy. In 40 years of career, you see quite a number of phenomena, and it was strongly in sensing. And actually, this was like tentative, but in the last times I've taught this course in a semester, I usually reach this inertial sensor business as well. So what about lecturing? Hissin 1 says that, yeah, we have exercises today, and then tomorrow afternoon from 2 to 4, we have lecture, but that's not how I plan to do it. Yeah, I have this 4-hour slot, or I should rather say 2 times 1.5 hour slot. I usually plan to do a 1.5 hour period. So if we start now at 4, we'll finish at 5:30. And tomorrow we'll maybe start at a bit later than 2 o'clock at 2:15. So let me write that down immediately. So where is my pointer? And black. So Monday, yeah, 16:00 to 17:30, and then Tuesday from 14:15 to 15:45. Is that correct? Yeah, I think from 4 to 6, from 2 to 4 is the reserved slot. And that's because I have another lecture from 1 to 2 before. And I usually need a bit of time to, at least complete the recording of the previous lecture. My computer is not ready to give the lecture. I would be, of course, but my computer is not ready. Yeah. So, and then, so lecture discussion, how do we share that? So I'll just progress with the lecture. And then when I see that we have enough material to do some interesting exercises, I will put online some exercise sheet, and then you have a week to work on those exercise sheet. And a week later, we'll talk about those. And that could be on Monday or on Tuesday. Now at the beginning, there's not much material, so I cannot hand out an exercise sheet today. Maybe tomorrow, could be, maybe only next week. And so be ready to participate on both days. Then also we have this interesting issue that we are using 2 lecture halls for this lecture, because the faculty is totally crammed and cannot accommodate all the wishes of all the professors. So today is, this is this 101-00-010-14 room, seminar room. And then tomorrow we have, if I remember well, on 051-00-031 seminar room. I hope that agrees with what you have extracted from Hissing 1. Is that correct? I sometimes I'm confused by 51, this building, or 52, the one next door. You knew where to come today, so where would you have gone tomorrow? Who wouldn't have known? Oh, yeah. Okay. Thank you very much, Jonathan. Yeah. So tomorrow we'll be in this other seminar room, and I hope we will not be too packed there. Yeah, I'll have to accommodate with that. And maybe I'll be standing there. I don't know, because today I already had 2 hours of lecture and many meetings, so I'm happy to be sitting a bit. Yeah. So I hope I have enough visual contact with you. Yeah. So this is how it's gonna go, and then I will not grade you, yeah, but I will at least evaluate your participation in the exercises. So I expect you to present exercises, to sit here and then scribble your solution, as I do scribble here on this trackpad. It's easy. You will very quickly grasp how this goes. I've seen that happen before, and I will also ask you to upload, your sketches or your solutions beforehand. But I will, of course, give you the details of how this is going to happen. Yeah, we have Ilias has this opportunity to upload sheets, and then I can scan through them and see who did what, and then decide who might present an interesting solution. Yeah, and so the condition for obtaining the ECTS grade of this entire course, the 6 ECTS, is that you participate sufficiently in the exercise, and that means that you work on at least 50% of the problems that I give you. Yeah. You work on those. It doesn't mean that you solve them perfectly, yeah, but I need to see your effort, yeah, the mental effort, and having dealt with the thing. And maybe that your idea is wrong. That can happen, misguided by some intuition, wrong intuition. That's no problem. It will not count as wrong. Yeah, I see your effort, and then we correct that effort. Yeah, and based on your thinking, you have also evolved to a higher level of understanding. And then I will also expect you to present a representative share of solutions here. So if we have, let's say, currently there are 28 people registered for the course. If we have 28 problems, then everyone needs to solve one problem. If we have 56 problems, then everyone has to work for 2 problems. If we have many dropouts, and at the end we're only 14, then it means that you have to solve 4 of those if there are 56 problems, and so on. Yeah, simple calculation, and it's not exact. Plus minus some standard deviation. Yeah? That's not a rigid scheme. Yeah, so this is how this goes, and then we will have some examination at the end. But that end is in September, or the course ends at the end of July, of course. Yeah, and there will be 1 semester week break around Pentecost, somewhere in June. So one break, and so we have 13 weeks of teaching this semester. And then, well, you have your examinations and preparation time and so on. And usually I do the examination in September, and that will be an oral exam. So no written problem solving. It's checking whether you got the ideas, understanding. So the problems that we solve here are not for preparing you for an examination. It's for preparing you for understanding. And that's why the discussion is very important, that we talk about possible misunderstandings or other aspects that may not have been addressed during the lecture and so on, that establish a solid basis for you. Good. Yeah. So I will always bring printed scripts. Yeah. The second chapter is a bit thicker. Yeah. Then there will be other chapters. Those who know me, know that I like mathematics. Yeah, and I like quantitative understanding. Yeah, I mean, talking about things is good, but evaluating things is better. Because you need not talk about impossible things, and or you need to talk about them shortly, just to say that I'm sorry, there's a flaw, because you're a factor of 1,000 off, and it can't work. And so that's important. And so I will sometimes bring additional material, and of course I will give you exercises, and I will tell you when those are available, and they will be available on also on the Ilias page. So let me see, Ilias is shown here. Yeah. So what do we have? Yeah, you probably have seen that we have a folder for homework problems. So I will deposit my next sheet in there, and then you'll get an email, saying that the sheet has been uploaded. There is also a platform for discussion, exchanging information. That might be among you, if you would like to put a question out there. Does somebody have a hint about, problem such and such, or you have another source for, I don't know what, somebody might respond. If there is additional lecture material, maybe the occasional paper about a sensor, I might deposit that here. Here is organization. So I deposited the information that you received by email also in there as a PDF. And then I'll add to the weekly recordings at this page here, on this folder, on this resource. So about half an hour after the lecture, usually the recording is transformed and compacted. The MP4 file is compact enough to be uploaded, and then you can listen to it again and make sure that the thing that might have escaped you during the lecture can be revived. When you ponder a problem and can't remember anymore, what is that thing? Here is the answer. Okay. Yeah. Then, am I really recording now? Where is this recording page? Pause recording. Yes, I'm recording. Okay. So I'm confused for a moment. Yeah. So then, what additional resources are there? So there is a book, CMOS MEMS, which I think we have in the library. It's from Wiley, VCH, compaction or compilation of chapters by eminent colleagues of mine who have contributed that. There is a book by by Simon C. I don't know Chinese, but in English he's usually pronounced C. I'm sure that people from China will object. Semiconductor sensors. It's an old book from 1994, I think. But it gives you broad ideas. And then there is a practical MEMS guidebook by Corvink and Paul from more recently, not very recently, that also provides a number of ideas. It's also available in the library. And then, of course, there is professional literature, journals, and professional conferences that advance the state of the art. This is, of course, a living subject. It's not an old traditional closed subject, but it evolves strongly. So let's go into chapter 1. Or first, let me ask you whether you have some questions about procedures or examinations or time planning. So let's go into chapter 1. So CMOS, I explained, is a technology. CMOS technology, one says, it means complementary metal oxide semiconductor. This is the technology that allows microelectronic companies to produce integrated systems for doing a lot of digital signal processing, like in a computer, the CPU, or the graphical processing unit, or the DRAM or the SSD chips. All those memory chips are based on complementary metal oxide semiconductor devices connected in an intricate way to make a big complex system. And we will see in chapter 2 a cross section through a CMOS device, and we will see how it evolves so that we know what materials are involved, and then we can think about what sensors, what MEMS we can make out of those. So CMOS means complementary metal oxide semiconductor. So complementary to what? Well, to itself, because there is within CMOS there is NMOS, N-channel MOS, and PMOS, P-channel MOS. So there are N-channel MOS FET transistors, metal oxide semiconductor field effect transistors. That's one polarity, which require one kind of gate voltage to be switched on or off. And then the PMOS are complementary to those, so that when the NMOS are on, the PMOS are off, and vice versa. And that gives you a dramatic diversity of logic options to implement logic circuitry. Of course, those seemingly digital devices are also used as analog devices because they have some continuous response as a function of the control parameter, the gate voltage, for instance. And that continuous response is used by analog circuit designers excessively to make amplifiers, to make filters, to make A to D converters, and so on. So that's an art which also resides in the understanding of CMOS devices. So the understanding of the CMOS devices per se, how a field effect transistor works in mathematical detail, is not the subject of this lecture. I teach that in my semiconductor course in the 4th semester, reasonably deeply. And now this is not necessary to understand the rest of this lecture. So the semiconductor physics, that very deep physics, is not so deeply necessary here. So this whole CMOS started actually, now it's, of course, now it is the mainstream silicon technology to fabricate in microelectronic systems. There's also bipolar technology that competed for some time with CMOS, but you can't control your devices so well, you can miniaturize them so well, so CMOS won. And I say also silicon because silicon one also. There are other semiconductors like gallium arsenide, yeah, which have just in certain ways better properties for optoelectronics, for speed, for mobility. Yeah, but it's more delicate to produce, so silicon one. Yeah? And so the big companies nowadays, the really big companies are silicon microelectronic companies. This started in 1947 with the invention of the first transistor. There are pictures of this device by Bardeen, Shockley, and Bratton, I think. Yeah, so a point contact transistor, some kind of pyramidal silicon piece standing on some surface, and of course, for some mysterious reason, this produced some effect that was never observed before, some diode or transistor effect, and so that was quite revolutionary, and this evolved at high speed, and from this big thing, that used this, that was this first computer. Now we have, of course, shrunk this by generations and generations of advancing technologies to incredibly small sizes. This progressive shrinking is called Moore's law. You have certainly heard that. Every year 1.5 times smaller or something, or more power, computing power, so much more computer power per area, or electrical power consumed per area, and so on. I mean, there's a lot of numbers that you can read up. If you Google Moore's law, then you will see all kinds of variants of that Moore's law. And the big companies that do that nowadays, I mean, there are big companies in Taiwan, TSMC, and I'm writing that first because this is the most advanced one. Even Intel, has sometimes a hard time in keeping up with TSMC. Intel is a big company in Oregon and other places in the world. They used to be the absolute top-notch player in this field, but TSMC, Taiwanese semiconductor manufacturing company, is now producing chips for the entire world. And that's also why people are a bit scared about mainland China's policy. They want to bring back, Taiwan, into their system, and then the West fears not to have the chips anymore. So there's, with all resources, there are geopolitical aspects also, like wheat from Ukraine or Russia. It's a geopolitical thing. People are fed globally nowadays, and they're also fed globally with chips. So that's why we look at all those companies in the world. And then there is one big company missing now that has grown very fast and very successfully. It's Samsung, in Korea. They make also very advanced technologies and very aggressive approach. Very successful. But then you have all kinds of others like Infineon, NXP, Global Foundries, Fujitsu, NEC, and so on. You certainly have heard these names. The semiconductor revenues are much higher now. That's an old number. So let me quote 2021. That's $585 billion US. So billion is in German Milliarde. Don't be confused with billion, and the progression of the numbers is in German Million, Milliarde, billion, then Billiarde, and then trillion, and so on. And the English language uses million, so they agree here, and then they say billion here, and then they say trillion here. So this is the corresponding, and then I think quadrillion and pentillion and something like that. I'm not sure about those. And so when you read sometimes newspapers and read these numbers, be careful to think whether something has been translated from another language by a journalist who doesn't make the difference of thousands. Yeah. So here is always a factor of 1,000. And so if you're off by 1 or 2 lines, you may be off by millions. Yeah. It's tough. Yeah. I saw some horrid numbers, horrible numbers recently that said that something was trillionen. Yeah, the journalist wrote trillionen. Yeah, the original number was trillion. Yeah, yeah, which is a difference. Yeah, but they don't make the difference with the zeros. It's only 3 zeros. Yeah. After this can't be a big difference. So sorry, I'm joking a bit about journalists. I'm not the first one, though. So 508 milliarden US dollars. That's the recent number, and this is from Gartner, famous company that does business analysis, worldwide business analysis, and they are specialized in semiconductor business. Then there are related technologies. I mentioned bipolar technology. There's also CCD technology, charge coupled device technology. Charge coupled devices were devices or are devices that are able to record light, images. But don't think that you have a CCD in your camera here. This is also CMOS now. And CMOS, again, 1, because it can be integrated smaller. You can have more pixels per area. It's not as efficient as a charge coupled device, but much more handy. And then you can also read out the data much easier. In CCD, you had to read out lines, and at the end, you had some converter that converted this. Very complicated circuitry. But for advanced systems, astronomical cameras that need to record every photon, CCD is still good. And of course you have memory technologies, and all this CMOS is actually made for mass markets. The investments are huge. Companies cost billions, milliarden US dollars, $5 billion for a company, for a fab. And Intel has many of those. So that investment must pay off. And it means that you must produce many, many wafers of silicon with many quadrillions of chips, and then you sell them for the price they have. And then you can get the money in again to build the next fab. That's how the business goes. Then you also know what MEMS is, micro electromechanical systems. That's the word. And in German, we say Mikrosystemtechnik, microsystems engineering in English. MEMS engineering, actually MEMS technology is very well widespread. And in Japan, actually they prefer to say micro machine technology. That's interesting that different areas of the world have different flavors to the same thing. They mean the same thing. But because Japanese they're very strong in machinery, robots, they said, okay, let's make small machines. And these are micro machines. The Germans are maybe the system thinker, the philosophers. So you cannot see that simply. This is a microsystem. It's very complicated. If you make it more complicated than that, then people will start believing that it's very complicated, and you are the know-how bearer. Americans are maybe more pragmatic. They say, what can it do? Electro, mechanical, micro, let's concoct that into a word, micro electromechanical system. So a personal interpretation of these different names. And so these are systems that rely on micromachining methods in all 3 cases, in all areas of the world, to carve structures out of silicon or of thin films. These are systems that are able to transduce a signal from one signal domain into another domain, a motion into an electrical signal, a temperature into an electrical signal, a magnetic field into an electrical signal, or an electric signal into a motion, a resonator. What do I know? So these are transducers, and so MEMS are always more than just electronics. Now the industry has coined the name more than Moore also to say that it is interesting to add other functionalities to microelectronic chips, and that this is the way to make, to create more worth for the customers, and of course from the company point of view to make more money to survive. So this is the more than Moore, because the shrinking of the microelectronic chips doesn't work anymore as well as it did 20 years ago. These lines don't continue that fast. There have been slower and slower slopes, and then we are reaching really fundamental limits with gate length of 3 nanometers. I mean, there is not much left. An atom has 3 angstrom, 0.3 nanometers. So 10 angstrom diameters, large microelectronic structures is pretty close to the limit. So you can still squeeze out a bit more by design, but you can squeeze out much more by adding additional functionality. And so in a sense, it is interesting to say that MEMS give senses to microelectronic systems because they can sense mechanical, magnetic, radiant, thermal, chemical effects. And that is like our brain, that is a computation unit, roughly speaking, neuronal computation unit that is fed by sensory signals to conclude that, oh, I should withdraw that hand from this location to survive. And so this is what happens here. A transduction effect in German is called Wandlereffekte. And Wandler is a transducer in English. And microtransducers is another name to say microelectromechanical systems. This company, what was that? This conference that I named here, Transducers, is about sensors and actuators. Okay, so what is the history of MEMS? Actually, MEMS was, I would say, pretty much invented in the United States, by people who worked in the microelectronics industry. Some curious minds who said, okay, can't we make other things with what we have here than just ones and zeros or so, or analog circuitry? And so they had this non-purely electrical engineering look on microelectronics, and actually it started in the 60s, but then I would say it had a first eye-catching paper that really caught people's attention. It was a paper by Kurt Peterson, Silicon as a Mechanical Material. So far, silicon was a microelectronic material for conducting or not conducting. And believe me, when I was a PhD student and wanted to go into a postdoc, I wanted to go away from my subject, which was surface magnetism. It seemed a bit narrow-minded to me, and I wanted to do something of greater importance. I said, okay, why don't I go into solar energy, photovoltaics? And so I applied for a grant at the Swiss National Foundation, and it was about some solar energy research at the Fraunhofer Institute here. In the early 90s, I was here in Freiburg for a first time, before going back to Switzerland, before coming back again as a professor here. And my professor, my PhD supervisor, said, Oliver, everything is known about silicon that's not a research subject. Yeah. Okay. Well, I thought it was maybe not the case. And I'm glad so. Yeah. So I'm no longer active in photovoltaics as I did during my postdoc. I went back into ETH Zurich to work on then technological things, doing with silicon. And it was MEMS, the new area of MEMS in the early 90s. So not everything was known about silicon. And today, not everything is known about many things where people, old guys, may tell you that it's all known. Yeah. So if I ever tell you that everything is known about something, be critical and say, maybe there is still a lot in there. Yeah. There's more layers to be discovered. Yeah. So in the 60s, actually, there was a very first paper that said, okay, I could actually, and I can draw this. Yeah. So I'm sure you have seen the cross section through a field effect transistor. Yeah. So I draw that in many lectures. Yeah. So here we have a gate. Let me hash that. The gate, which has a potential. And then here we have the so-called source, and here the drain. They all are contacted. So here there's some contact, and there are some insulating layers also. And this below here is silicon. So it could be, let's say, P silicon, then this is N silicon, and then here we have this little channel. And a current can flow from the source through this channel to this drain if the gate has the right voltage. Now, Nathanson said, maybe I could make some sensitive device by making this gate, which in the usual transistors is really stuck to the silicon by some insulating layer. So this little white layer here is silicon oxide in the early CMOS technologies. 100 angstroms of oxide. And then there comes this highly conductive gate material on top. And he said, if I made this gate suspended, and I give it a potential and it is allowed to move, maybe I can see this in a modulation of the current. And it worked. So this was the suspended gate sensor, which was able to detect vibration because the chip below was shaken, this gate was moving, and so this was the first motion sensor or mechanical sensor, where the gate material, which was at that time, or for many years, was polysilicon. At the time, I think he made it out of metal, gold. And this gate that is usually rigidly stuck, was now a mechanical structure. So a micro-mechanical structure. Certainly not as micro as we do it today, because the technology was not as advanced, but he had these ideas of, removing something below the gate. So this was the first idea of sacrificial micromachining. Then there was this gate, this floating gate. Then another subject that I remember well was in the 1970s, a gas chromatographer on a wafer that was developed at Stanford University, a wafer-sized device. I mean, the wafers were smaller then, not the big ones, small wafer, but still it was a whole system, a chemically measuring system on a wafer produced with micromachining. And then Ken Wise, who was also, I think, at Stanford University initially, then at Michigan, University of Michigan, Ann Arbor, he produced so-called silicon probes by using diffusion technologies and metallization technologies and micromachining technologies, and making very fine needles to use in neural probes. And we are still developing neural probes nowadays. In my group, we have a large effort led by Dr. Ruto, who does silicon probes, and he has a lecture about silicon neural probes. So this is also an old effort that has survived the test of time. And in the late 1980s, 1987 or so, Longshan Fan and Yu Chong Tai and Richard Muller of Berkeley published the first rotational thing, a motor that was an object that was rotated by electrostatic forces on the surface of some silicon chip. A 2D motor. I mean, it didn't move anything. It just rotated. And it was gone, probably broken. But anyway, it was fantastic because I mean, these American universities have excellent PR departments. So it was in all the journals, and then people start dreaming. Micro machines, really little things that can do complicated things, and so that started the whole movement. Well, MEMS technology now has moved into different directions. We don't see these little micro gears, micro motors, and so on nowadays. But it was kind of a trigger to say other things are possible. And now we earn the return on that enthusiasm. Yeah, and so in the 90s, actually, I started in MEMS in 1992. There was a real explosion of ideas. Departments were founded in all kinds of universities, and companies started, exploiting that. They saw the opportunity to do inertial sensors, to do pressure sensors, to do all kinds of things, and that has grown into a very large industry nowadays. So here are some numbers about the industry. This says $1 million. So this would be 10 billion here. Actually, it's kind of controversial. I don't know what to believe these nice slides. They're very colorful and they usually grow. And this is from Yole, another one like Gartner, another analyst of the market. And so, I looked up the numbers yesterday to see what was it in 2021. And what I found also from Yole was the number of, 2020 was 10.6 billion, and it has grown by so and so many percent to 13.8 in 2021. Well, 2020 was the Corona year, the first one, so business was down in many cases, and then that caught up. But it's below the level that I see here, and I don't know what exactly is there. What you can keep for sure as a main message is that there are now products sold in this area of MEMS and CMOS MEMS in the area of in the range of 10 billion. That's sizable. And big companies like Bosch make maybe 1 billion out of those. And then there's smaller companies and then very small companies who earn much less. And the growth tendency is definitely there. I mean, there's no doubt about that in the long term. There may be economic downturns, but this tendency of implementing functionalities, sensorial functionalities into systems is just a natural trend. There's the Internet of Things, the Trillion Sensor Initiative. You have lots of Industry 4.0. So there's many different names that always, have this data-heavy approach to life in them, because we can use the data, because we have the computational power, and therefore we need the MEMS in there. Yeah, so why to do MEMS with CMOS? I mean, you can do MEMS differently. You can take some polymer layers and do, interesting MEMS. Professor Zengerle does that too. The MEMS technology area has evolved into many directions. There are ceramic MEMS, there are polymer MEMS, there's all kinds of different hybrid technologies. So why CMOS? CMOS is simply attractive because of the mass market aspect. Yeah. There is a huge experience with process technology that can be beneficial to translating an idea into objects that can be reproduced reliably. And so if you have an idea for a smart thing that will only be applied in very exclusive situations, you might have a niche product that can sell expensively because somebody wants it, but this is not going to be a mass market product. So CMOS in that case is not the good thing. But if you have sensors that might benefit many people, like I take an example that I know well, Sensirion, a company in Switzerland that was founded by one or co-founded by one of my ex-PhD students. Well, they had the idea to do humidity sensors. And humidity sensors can be put in many places, in all air conditioning system, in all little weather stations. They could be put into phones to know about the humidity that surrounds you, like other gas compositions. It's something that could be produced in millions. And so they said, okay, let's try. Yeah. The standard company don't want to do that. Yeah. So let's do it ourselves. Yeah. We can conquer a market. We can be cheaper because CMOS can be fabricated in large numbers and therefore cheaper than these little fuzzy things that they produce basically in one-by-one technologies, hand-wise technologies before. And so now Sensirion has a revenue of about 250 million Swiss francs per year. And half of that is for humidity sensors. Other technologies have complemented their portfolio, other mass market ideas, but it's all produced, or most of it is based on CMOS technology. So they're a big customer of TSMC in Taiwan, who produce the wafers with their systems that they then do micromachine and package and all the special know-how that they have to make interesting sensors out of this. So mass markets can be addressed. There are very large companies who do that, like ST Microelectronics, Analog Devices, Infineon, Motorola, Texas Instruments, and so on. Texas Instruments is, for instance, well known for the DMD, digital micro mirror device. Projector up here may have a DMD chip in there. 1,000 by 1,000 or 1,280 by 768 little mirrors that can be flipped to either side, to white or dark, many times per second, with many filters passing in front and to have a color image, and or three of them illuminated by three different colors. And below that is CMOS technology. And there is some additional micromachining technology above the top. It's a very, very successful device. Analog Devices is well known for inertial sensors, acceleration sensors and gyros, rotational angular rotation sensors. So, but then there are also small and medium companies. I mentioned Sensirion before, with 250 million of revenue per year. You're a pretty small company in this world. Micronas is located here in Freiburg at Hans-Bunte-Straße. They make a lot of micro magnetic sensors, magnetic sensor chips, very successfully. There is another company in Switzerland, in Belgium, in 2 locations, Melexis, who does similar things. Allegro is also a magnetic sensor company. Austron Mikrosysteme used to do many things. Now there are a lot in light sensing, but also magnetic sensing. X-FAB has a large portfolio of different technologies that they offer to many customers. And then there are really niche market companies that are less well known, Neuronexus, Atlas Neuroengineering, for instance, are two companies who produce neural probes. They make a living of producing neural probes. Now, that's not a mass market. Yeah, there's not so many people who need to stick a probe in their head. Yeah, this is a research market. Yeah, by a dedicated group of researchers who use those probes to resolve biological questions having to do with the health of the brain and the working of the brain and therapies related to those mechanisms. So there's a number of companies, and Atlas Neuroengineering actually is also a company that I helped co-found. There's a little subsidiary here in Freiburg in my lab. They do some work in this area here. But of course, there are drawbacks with CMOS. There are advantages that I outlined that many people use beneficially, but then there are drawbacks because CMOS technology is something very restrictive. It's certain kind of architecture, certain kind of materials, and so you cannot dream too wildly because those wild dreams can't be realized. So it's better to know what CMOS can do and to dream within that framework, but you still can be very creative within that framework. Having some rules doesn't mean that it is necessarily worse than having no rules, because when you have no rules, you don't know what to do because the world is so wide. If you have rules, then you can say, okay, if I do that, maybe I can twist it a little bit, and then you are being stimulated. Yeah, the limit is kind of a challenge to go beyond. I always use the analogy of music. Yeah, music is subjected to heavy rules, at least Baroque music. Yeah, if you know Baroque music by Johann Sebastian Bach, yeah, sure most of you have heard about him. Yeah, if not, please Google him and listen to some of his music. There are beautiful pieces. Yeah, and when you go deeper and look how he composed his music, a fugue, yeah, how this counterpoint is constructed, it's hugely complex. There's so many rules, what is allowed and what is not allowed. And yet, beautiful music comes out. So let's play the music of CMOS to make some nice structures, nice systems. So I have here a few examples now that show you how some, wild dreams can be translated into within the limits of CMOS technology. So here you have a humidity sensor, a classical humidity sensor from the 18th century, invented by de Saussure, Horace Bénédict de Saussure in Geneva. And one day he went to his wife and said, here's your hair. Yeah, your hair curls up, doesn't it, in humidity? It means that humidity has a mechanical effect on it. Yeah. So he put it here on this machine, from down here up to some axle. Yeah. And as the humidity changed, the hair would pull more or less on that axle, which was kind of put under tension by a spring. Yeah. And if you attached, well, that's what he did. He attached a lever on that axle to monitor that pulling force against the spring. Yeah? And so he had a humidity sensor based on a polymer material. Keratin of hair is humidity sensitive. So it's a mechanical, chemomechanical sensor. And so how does one translate that into CMOS? Well, the company Sensirion that I mentioned before does it basically, simply the following way. So they have the silicon chip, and then of course there's insulators, and then there need to be some electrodes. So I draw an array of electrodes. And in 3D, these are all long lines, okay? So rub, let me just draw one edge. So these are long lines, and they are actually lines that are consisting of two systems of lines. Yeah, every second line is connected, and the other lines are embedded, interdigitated, as one says in the language, between. Yeah, so again, you can think of this line, this line, this line to be connected together, and then the second line back there. And I have to draw it totally. Duck, duck, duck. This one connected to this one. Yeah. And then there is another one down here. Yeah. So it's connected to here. So we have 6 lines, and 3 of each are connected together, and they're alternating. Yeah. So they form a capacitor. So if I now add some polymer material on top, something like this. Yeah, so polymer covering this whole thing, a hygroscopic polymer that absorbs water and can release water from the ambient, which absorbs more water if there is more water around when the humidity is high, and releases water when it's more dry out there, becomes drier itself. Then the capacity between these two electrodes, the capacity between these 2 electrode systems is changing as a function of humidity. So this is a function of humidity, or I should say relative humidity. Yeah. Oh, can't write here. So I'll write it somewhere else. Is a function of the relative humidity. So that's the principal sensor ideas. Now you say, where is the CMOS? It's below, of course, because to detect changes of capacity, you may need a system. And so on this same chip, there is a lot of microelectronic circuitry that does exactly that thing, to measure the capacitance, and then to induce or deduce or infer the humidity that is reigning around the chip. And you see that this chip is somewhere embedded down here. There are some contacts for digital and analog outputs, and then this package, this polymer package that surrounds the whole chip, and surrounds this orange humidity sensitive material, protects the whole chip from the environment, except at this little central hole where humidity can pervade this orange substance. So the humidity has access to the sensor chip here, but the rest of the sensor chip is well protected against the humidity. Humidity has some corrosive effect, and so it's a contradictory challenge to let the humidity go to the chip surface and at the same time protect the chip against the adverse effect of the humidity. So that's know-how. That's how you earn your money. Other people try and can't succeed, and you succeed in solving a problem like that. So this is a way to do, and this is also a chemical sensor. But it's no longer a chemomechanical sensor like the old machine. It's a no, it's not electrochemical. It's chemoelectric sensor, maybe chemocapacitive. And it is very good. It measures from 0 to 100% relative humidity. It consumes very little power. It works at different temperatures. It's fairly fast. So typical time constant of seconds. I don't know what the newer sensors do. And this sensor here actually is an older model. The current model has a size that looks about, or a shape that looks like this. And if I remember well, it's 1.3 millimeter long. It's 0.7 millimeter wide. and it's I don't know, 0.6 millimeter high or something. Yeah, everything included. Yeah, packaging included, contacts included. It's dust, sensor dust. Yeah, it's fascinating. Yeah, and so you have millions of sensors in a little bowl. I remember a talk when Markus Graf brought us so different containers with sensors, and then the last one is just a little. What was so big was then only so small. Yeah. Okay. Then what about another sensor idea, the compass? Now, a compass is a magnetic field sensor. It is fine-tuned to measure the Earth magnetic field. The Earth magnetic field measures about 25 microtesla. So the B, the absolute value of the Earth magnetic field is 25 microtesla. It's not a strong field. But when you expose a magnetized needle that is well hinged, with little friction on some support, then this needle will, with its north and south pole, will just orient along the direction of the magnetic field, B. And so, because those magnetic fields emerge from the Earth in a certain direction that has something to do with the axis of rotation of the Earth, roughly. You can basically say where is north, and that's very handy when you are out there in the Canadian wilderness and or in the Alps. Now with GPS you have another way to find your way. But that used to be my childhood's remembrances out in nature. We had to use the compass, and compass is no longer such an this mechanical compass is no longer such an important device, but magnetic field measurement is still an important challenge. Every car has 10, 20, 30 magnetic field sensors built into its system. Many reasons why currents need to be measured, positions need to be measured, and this can all be done with magnetic effects. So this simple magneto-mechanical system, or I should say magneto-mechano-optical system. The readout is optical. So it's a magneto-mechanic optical system. Now that is nowadays a galvanomagnetic system. Galvanomagnetic. Galvanomagnetic effects are exploited, and that means that galvano means always applying voltages or earning voltages. Magnetic means, of course, magnetic field. So some electrical voltages, are related to magnetic fields. That's what galvanomagnetic means. And this is a chip by Micronas, and it's something which people who have heard other courses of mine, of course, know very well. It's based on a Hall sensor. So in this chip, very simply sketched here, that is embedded here with its contacts on the surface of the chip. So let's say this is silicon with all kinds of circuitry, all around. There is a so-called Hall sensor, which is a diffused region, an N region that has been diffused, like you use it also for transistors, and that has been equipped with 4 contacts on 4 sides. And then a current is sent through the device, and a Hall voltage can be measured between these orthogonal devices. In what case? When a magnetic field B pervades that chip. The magnetic field goes through almost anything. If you do not want the magnetic field to go through something, you have to apply special magnetizable materials, permalloy or other mu metal, very specialized metals. But so magnetizable metals. But otherwise, the magnetic field goes through anything, yeah, through this table, through this plastic, through this aluminum, yeah. So it's easy to measure the magnetic field. Yeah? And so all that needs to happen is that this chip is crossed by a magnetic field, and it will provide an output, some output, some analog output, you know, V, Hall, amplified, digitized, or whatever. Yeah? And CMOS technology makes it possible to integrate this Hall sensor, a very simple design, on this complicated system. The Hall sensor itself is not that simple, actually. Yeah, we will learn that we need more tricks to make a good magnetic field sensor. This is the most basic idea, and it will only have a resolution that will never let you resolve the Earth's magnetic field. You need to apply additional tricks to go down to that limit. So here is again a system that translates a traditional system into an electronic system, relying on CMOS technology. And here actually it's simpler, yeah, because you can really package that sensor all around hermetically. There is no danger that humidity ruins the chip, because the humidity must not go there, and you can, light must not go there. It's a black thing. Other, chemicals or so must not go there. So this is a fantastic system that you can really package well, and the signal that you want to measure reaches the sensitive area by nature, so to speak. And so this measures actually 30 millitesla ranges, or 100 millitesla. So many times larger signals than these Earth magnetic fields. But it also works over a large range of temperatures. It's robust against mechanical stress. It works fast. Whereas this needle needs seconds to find the north. This will find the respective direction of the magnetic field immediately. And many variants, 2D, 3D sensors that are based on this kind of technology. So we'll learn about those in chapter 3. And here is a mechanical idea, a force sensor. This scale is made to measure the weight, mass 1 versus mass 2, to compare masses. We'll just flip to one side if one mass is heavier, or you can measure an unknown mass by putting in calibrated masses. So this is how my grandmother measured, or had her vegetables weighted at the market in Graz. I remember that well, adding these weights until they knew what she had to pay. And so one of my students, Mark Baumann, as part of his PhD thesis, made this micro scale, which is composed of a supporting chip, a glass chip, and then a silicon chip made in CMOS technology that is bonded on top of this glass chip. The glass chip has a little cavity, and the silicon chip can be microstructured, as you see here. So let's imagine that we have here one continuous piece that is kind of a rotational axle, and then there is this orthogonal piece that is attached in the middle to that axle, and it's kind of like a wippe. How do you say wippe in English? This the balance, or where the children like to sit on either side, and seesaw, right? A seesaw. It's kind of the seesaw principle. And if a force Fa is different from the force Fb, the seesaw will go in one direction. And because it's an elastic material, this inclination will be proportional to the difference in the forces. So, and well, actually, he made several variants. He also attached another piece here, and then, made a force measuring device. So with a range of 50 Newton, and it was fairly robust, because when you apply excessive forces, then simply the seesaw will settle at the bottom, and then it's very stably sitting there, and nothing can happen to it. And of course, it's only a force sensor for one force direction. In order to pull, you have to attach something, whereas to push is easy, of course. So you only need to establish contact to push. So an academic idea, microscale, as I like to say. So in MEMS, we address not only electrical signals, but non-electrical signals. And I just enumerated some of those here. You don't need to learn them by heart. It's not going to say, tell me the 5 entries on slide 17 of chapter 1. It's more kind of common sense. Mechanical systems can be position or changing position, that is displacement or displacement of orientation, rotation, tilt, level, nearness, proximity, as it is called, proximity sensing, velocity, angular velocity, so the rate of change of these signals appear, acceleration, the next derivative, angular acceleration, deformation. Deformation means also stress. So stress, force, strain. These are all things that can be mechanically measured. Shape is also something, and influences that lead to mechanical signals, of course, can be localized forces, contact, inertial forces, the fact that something has a mass and can't move as fast as the object to which it is attached, causes immediately maybe some forces, relative forces, moments, pressure. These are forces acting on surfaces, acoustic waves, or mass flow. Also causes mechanical forces. If a flow of some substance goes over a surface, there's, because of the viscosity of this fluid, the fluid pulls on the surface. There's friction within the fluid. This friction is called viscosity, and so there's momentum transfer, as the physicist will say, and that means that if you have some flow in the pipe, the flow pulls on the pipe, and this can also be used. It has been used to make mass flow sensors, mechanical mass flow sensors, or as it is called, shear stress. So I can sketch that. If you have the substrate here, and you have here some flowing fluid, the fluid velocity, if I plot the fluid velocity v as a function of this coordinate z, the fluid velocity will be increasing from 0. Here is 0, and then it will be larger and larger as we go away from the surface. And if this is a pipe with another or two planes with the fluid flowing in between, then you may have some parabolic fluid profile. That leads into the Hagen-Poiseuille law. You need to push to get the fluid through, and if you push, then of course you push also via the fluid on the surfaces with which it is in contact. So shear stress. But let me not get too much into detail here. Magnetic signals, the magnetic field, its magnitude, its direction, 3D direction, if possible, is of interest. And of course, there are influences that causes these magnetic signals, the Earth magnetic field, I said, technical magnetic fields, currents. So a current is a source of magnetic field, as you know. If we have some current flowing through a wire, This wire is surrounded by a circular magnetic field with a very easily described dependency on the distance from the current, 1/r. And so here is a magnetic field that we might measure with a sensor. I drew here a schematic Hall sensor. If we measure the field at a distance of this wire, we know what current flows through the wire. We have a non-contacting current sensor. Interesting. So the Hall sensors that I showed before are used to measure power dissipation by systems without aggressing those, without intruding those by making a direct measurement. It comes for free. This magnetic field comes for free. But also you could have, of course, magnets with some north and south pole. So I drew here a schematic thing. And if this is mounted on an axle, it can move up and down like a seesaw. For instance, in a switch, cluck, cluck, the two positions of a switch. Imagine that you have a little magnet in there. If you move it from one position to the other, the magnetic field pervading space will also rotate with the little magnet. And now you have beside a magnetic field sensor that senses that changing magnetic field. So you have an electrical measurement in a well-protected system that allows you to detect the position of the switch. So that's very handy because if you have rough environments, humid environments, harsh environments, as the industry says, you can make switches that are not directly affected by the harsh environment. In earlier times, times of my grandfathers and of my fathers, and even in my youth, a switch was a thing where a metal contacted or did not contact another metal. That was a switch. But those metals corrode in harsh environments, and at some point they're oxidized or dirty, and then they don't work anymore. Then you have to take them apart, clean them, and put them back together. You cannot do that with mass market products. So this is a way to do a mass market switch that is inherently reliable. Yeah, and we have radiant signals, electromagnetic waves. Of course, there is the visible light. There is to the other side the infrared and the ultraviolet spectrum, microwave spectrum, X-rays, very high energies, particle radiation. There's flux density, spectral composition, polarization, phase, coherence, all kinds of optical parameters that might need to be detected in certain measurement situations, instrumentation, and well, one can think of how to realize that. Detecting light with semiconductors is easy. Light is absorbed. It produces voltages, photoelectric voltages, photovoltaic in PN junctions, or it modulates radiation, resistors. And so detecting light is not difficult. And if you have light of different colors, light penetrates silicon to different depths depending on its energy. So you may have absorption at different depths, or you can even detect colors, distinguish colors by semiconductor devices, and it is being done. And of course, semiconductor light detectors are hugely widespread. Photovoltaic cells are nothing else than light detectors. But they are not fabricated in CMOS technology. They don't need any microelectronics integrated. They need high efficiency. They need some electronic structures, some grids to collect the current. But what is implemented there is, of course, also technological ideas that you find in CMOS technology, semiconductor technology. And so, of course, you have different sources of light, and and light can be used to directly or indirectly to measure things. You have also chemical signals, concentrations, partial pressures, acidity. So this would be some ionic concentrations or electrochemical potentials. That would be some, thermodynamically averaged properties of particle energies. We have also entropy, enthalpy, free energy. So that is energies that might change due to absorption or desorption or absorption of material, interaction of different gases with surfaces or materials, and those can also be measured. And there are CMOS compatible chemical sensors that can measure the pH concentration, the pH of a solution. And so we can think about that. But there are also other chemical sensors, like, for instance, those of Sensirion. They have volatile organic compound sensors. So the more complex molecules that are now filling this room. Some sweat, components have the smell. Yeah, these are so-called volatile organic compounds. And if you want to measure the quality of air, if you're able to measure those compounds, then you can say, okay, now is the moment to switch on the air conditioning, to give the people a good breathing again. And those volatile organic compounds, when they are depositing on or reacting with the surface, this reaction energy changes the temperature of some microstructure. Or they lead to a reaction that changes the conductivity of some material deposited on the surface of a chip. And if that chip has, again, microelectronic circuitry to drive it and to read out and to digitize the information, then it can be a CMOS chip. And Sensirion produces this kind of environmental sensors. So there's many ways to proceed. There's also thermal signals, temperature, heat quantity, and so on. And then some more elusive signals down here that I just mentioned for completion. The gravitational signal, that's more an inertial signal that cannot be distinguished from any other acceleration. We have some quantum mechanical signals that are not addressed by MEMS, but and even less so by CMOS MEMS. So with that, I would like to close here. It's time to finish, and then we will meet again tomorrow at 2:15 in this other room in building 051. So hope to see you there, and I wish you a nice evening. Bye-bye.